All right, so again, these properties are what we went over last week. Now these are properties of any function. All right, so I gave you the function notation over here because these are the rules that we follow no matter what our function is. Okay, if it's x squared, if it's the square root of x, the only thing that's going to look different is the actual function itself, right? But these rules are the same for whatever we're looking at. So when we subtract on the inside, okay, or we do a direct operation on the x, that's a horizontal translation, right? It moves it left or right. Now be careful. Again, it's always the opposite. So that's why I put the negative there. So if you have x minus 1, that means you're moving it to the right 1 unit. If you have x plus 3, that means you're moving it to the left 3 units. All right, and that's when it's directly attached to the x. So in function notation, you'll see it like this. In exponential notation, you'll see it up there with the exponent. If you're adding a value to the outside of the function, all right, so if you had a to the x plus 10, all right, that's a vertical translation. Now that translation is directly what you see. If you're adding, you go up. If you're subtracting, you go down. Okay, it's common sense for that one. If you throw a negative in front of your function, okay, so negative a to, negative 2 to the x, negative 5 to the x, that reflects it over the x-axis. Okay, so you would have it from the top. And if you're thinking about it, all you're doing is you're taking the answer and you're making a negative, right? So that's putting all your answers above the x-axis, and it's putting them below the x-axis. So when you see the negative on the front like that, it's a reflection over the x-axis or a vertical reflection. Okay, be careful. Those are kind of, flip-flop. If you're doing a vertical reflection, it's over the horizontal x-axis. If you have a negative attached to that x value, okay, up there in the exponent, that reflects it over the y-axis. And a good way to see that especially with our exponential functions, right, is we're changing the sign. So a squared, normally, you're a times a. But a to the negative squared, that's 1 over a to the x, right? So that's putting everything, that's flipping your x values, right, with your positives and your negatives. So that's a horizontal reflection over the y-axis, the vertical y-axis. Okay. Were there any questions about that from last week? I think we covered most of that. All right. So starting today, we're going to take a look at actual solving exponential equations. All right. So quickly, let me put this a little closer. All right, so this stuff you should have went over last year, but who knows how long ago that was. If you were already in lockdown, I don't know. So we're gonna go over the exponential properties first. Forgot how to spell. All right, so our first was addition and multiplication property. Now they're kind of tied together. So if you have two functions, two exponential functions, okay, and they have the same base, right? That base has to be the same, and you're multiplying them, then you can add their exponents together. Okay, a to the x plus y. Right. So if you had 2 to the 4th times 2 to the 5th, that would be the same thing as 2 to the 9th. Then we had subtraction and division. So if you had a to the x over a to the y, okay, we subtract our exponents, x minus y, right? And that, I mean, we've done it before. I'm pretty sure we've done it before. Okay, so if you had something like 2 to the third over 2 to the sixth, we would subtract them. It's always the numerator minus the denominator. So in that case, we would end up with an exponent of -3. Which brings me to my next property. Okay, anytime we have a negative exponent, that means we take the reciprocal. All right, similarly, if I had something that looked like 1 over a to the negative x, right? So if you had, let me make that look a little nicer. Okay, so if you had a negative exponent in the denominator, that would just put us back up in the numerator. Now, one thing I do want to say is be careful if there's a coefficient, okay? So if you had, I don't know, so if you had something like 3x to the negative second, that 3 would stay in the numerator, and the exponent and whatever the base that the exponent is tied to would go in the denominator. Oh, actually, that brings me to something. I'm not sure if I specifically went over this. Yeah, okay. But again, yeah. Here I'm calling it a, all right, but that's known as the base of our exponential function. Okay, so if you keep hearing me say base, I just mean the number that we're tying the exponent to. All right, so we got addition. Okay, and then I think there's one more. All right, when we're raising an exponent to another exponent. So if you have a to the x raised to the y, then you multiply your exponents, x times y. Right? And all this gets tied along with the negative exponents. If any of these exponents happen to be negative, then in math, we don't like negative exponents. They're kind of, undesirable. So whatever we have, we like to simplify so that we don't have negative exponents. Is there anything else? Before I move on, I don't think so. I think those are all my properties. Okay. Any concerns about that? And again, most of these you should have learned in Algebra 1 or Algebra 2. So it may have been a while since you've seen it, but they should be familiar to you. Okay, so now one method that we use to help us solve exponents is the fact that exponential functions are one-to-one. Okay, so remember, I think we went over one-to-one way early in the year. Okay, but 1-to-1 tells us that every input has exactly one output. Okay, so x to the squared is not one. X squared is not 1-to-1 because two inputs get you the same output, right? -2 squared gets you 4, and 2 squared gets you 4, right? So that is not a 1-to-1 function. So there's two things that come along with 1-to-1. The first part, which we won't see for another couple days, if not next week, is that exponential functions have an inverse. Okay, that's a property of a 1-to-1, right? When we started talking about inverse functions, a function has to be 1-to-1 in order to take the inverse. Okay, so we're going to see that a little later. The other part, for now, that the 1-to-1 property that we have, okay, let me see. So again, we have the same rules. Our base has to be greater than 0, and it can't be 1. So for exponentials, if we have a to the x equals a to the y, the only way that we can have that is if x equals y, right? And that's the key part, the key property that we're going to be using for the rest of today. Right, so a very, very, very basic example. Right, if you had something like 3 to the 4th equals 3 to the x, well, then we know x equals 4, right? There's only one way, there's only one number for x to equal, right? And that would be, it would have to be the same exponent. So x would equal 4. Okay, we could take that up a step. Okay, if we had functions, okay, as our exponents. So here we have some composite functions. But again, we would just be looking at the exponents. Right? So you have x minus 1 equals 2x, and now we would solve this as normal. Right? I would subtract x from both sides. So I'd get x equals -1. Right? And that's the only instance that we have. So here I have 2 to the -2nd, and here I would also have 2 to the -2nd. Right? And they have to be equal. Right? So let's take a look at something a little more challenging. Okay, so this 1-to-1 property is only applicable when we have the same base. Now here we don't have the same base, but we can manipulate the equation so that we do have the same base. So what we're looking for is bases that are prime numbers. Not always, but that usually helps. All right. So on the right side of my equation, I have a 3 to the x plus 1. All right, so this 3 is a prime number. There's not much I can do with that. But is there another way that we can represent the 9 specifically as an exponent with a base of 3? How can I rewrite 9? So I want the same base, right? So what would I have to rewrite 9 as? 3 to what power? Anybody? We awake? 3 to what power gets me 9?
To 2.
All right, 3 squared is 9. Thank you. All right, so now that we have the same base, we just look at the exponent, and then we solve. All right, let's take a look at some more examples. All right. So stop me at any time if you're confused. All right, this is what we'll be doing for the rest of the class, pretty much. Okay, so this one is a little different. Same concept, though. That's just a 1. Okay, so we need to do 2 things here. All right. So this part, well, I don't like to deal with fractions, and I don't want to get the 8 to be a fraction. That's too much going on. All right, so here we can use our negative property. Right, 1 over 2 is the same as 2 to the negative first. So I'm going to change 1/2 to 2 to the negative first, and I still have that exponent x. Now the 8, well, here my base is 2, so I want to break down the 8, so it's 2, well, 2 squared is 4, 2 to the third is 8. So here we have an exponent to an exponent, so I can rewrite this as 2 to the negative x equals 2 to the third. We have the same base, so now we just look at the exponents, right? So negative x equals 3, or x equals negative 3. All right, let's look at another one. All right, so here's one where we're going to have to do it twice. All right. So here we have 16 equals 4x plus 2. So for neither of these do we have a prime number. Okay. But you can kind of think to yourself, well, both of those have factors of 2 involved, right? So we're going to try to break it down to 2 to some power. So the 16, okay, that's going to be 2 to the 4th. Now be careful here. The 4 is 2 squared, and then we still have x plus 2 as our exponent. So I want to simplify this so that we have a single exponential function, right? So we're multiplying these 2 terms. So just be careful. We have to distribute this 2 to both of our parts up here in that exponent. So on the left, I still have 2 to the 4th. That's still going to stay for that. I haven't touched that. Okay, and then I have 2x plus 4. Right, I distributed that 2 to the exponent. So now that we have the same base, we're going to have 4 equals 2x plus 4. Well, in this case, okay, my x would be 0. Right, I would subtract 4 from both sides. I have 2x equals 0. So I get x equals 0. Now, you can always double check by plugging it in, right? That doesn't seem, 0 powers. That's weird. So you want to double check. So you go back and you plug. Well, 0 plus 2 is 0. 4 squared, that does get us 16. All right, let's do one more. All right, so the last one we'll look at, I have 1/3 to the negative x equals 27. All right, so here, so yeah, most of your first step is to find out what that base is going to be, your common base. Well, on the left side, we have a fraction with a 3 in the denominator, and 27 is a multiple of 3, so our base will probably be 3. So this 1/3 I can rewrite as 3 to the negative 1, and I have that to the negative x power. So just be careful there in your next step. 27, well, that's going to be 3 to the 3rd power, right? Because 3 squared is 9, times 3 again is 27. Here, 3 to the negative 1 to the negative x is just 3 to the x. So as long as, if you simplify sometimes, right, you don't really have to do much. Here we get x is equal to 3. Right, and going back to the original, looking at it, 1/3 to the negative 3, well, that would be a fraction to a negative, which means that we would flip this and raise it to the 3rd, so 3 to the 3rd. That does get us our 27. Any questions?